Hello, and welcome to Sleepy Stargazer, your tranquil telescope to the stars, where we gently explore the vastness of the universe, one calm, curious night at a time. From the quiet birth of distant galaxies to the soft shimmer of moons and planets, each story is told in a soothing voice designed to ease your mind, spark your wonder, and guide you gently toward dreamland. So, settle in, breathe deep, and let the stars watch over you as we drift through space together, one sleepy stargaze at a time. In the beginning there was nothing, not darkness, for darkness implies the absence of light, and light itself had not yet been conceived. Not silence, for silence suggests the possibility of sound, and sound required matter to carry its vibrations through space that did not exist. There was simply nothing, no time, no space, no matter, no energy. It was a state beyond human comprehension, a void so complete that even the concept of void itself would be inadequate to describe it. And yet from this absolute nothingness, everything we know and see and touch and breathe would emerge in a single, magnificent moment that would echo through eternity. The ancient Greeks pondered this mystery as they gazed upon the star-scattered heavens above their marble temples. They spoke of chaos, the primordial void from which all things emerged, and of Kronos, time itself, who devoured his own children. The Babylonians carved their creation myths into cuneiform tablets, telling of Marduk's battle against the chaos monster Tiamat, whose defeated body formed the heavens and the earth. In the sacred texts of countless civilizations, from the Vedic hymns of ancient India to the creation songs of the Aboriginal peoples of Australia, humanity has always sought to understand that first moment when existence began. But it was not until the 20th century, as the world emerged from the shadows of two great wars and humanity began to peer deeper into the cosmos with ever more sophisticated instruments, that the true story of creation began to reveal itself. It was a story that would prove more wondrous and more strange than any myth ever conceived by human imagination. The tale begins with a man named Edwin Hubble, working alone in the cold mountain air of California's Mount Wilson Observatory in the 1920s. As you settle deeper into comfort, imagine those quiet nights when Hubble would climb the narrow stairs to the great telescope, his breath visible in the thin air, his hands steady despite the chill. He was studying distant galaxies, those vast islands of stars that seem to float like glowing spirits in the darkness of space. What he discovered would shake the very foundations of human understanding. Through careful observation and meticulous calculation, Hubble noticed something extraordinary. The galaxies were moving away from us. Not just a few of them, but all of them in every direction. The farther away a galaxy was, the faster it appeared to be receding. It was as if the entire universe was expanding, like a balloon being inflated, with every point on its surface moving away from every other point. This revelation reached the ears of a brilliant Belgian physicist and Catholic priest named Georges Lemaitre. As the gentle hours of night deepen around you, picture this remarkable man, his mind bridging the realms of science and faith, contemplating the implications of Hubble's discovery. If the universe was expanding now, Lemaitre reasoned, then it must have been smaller in the past. Following this logic backward through time, there must have been a moment when all of space and all of matter were compressed into a single point of infinite density and infinite temperature. Lemaitre called this the primeval atom, though history would remember it by a more colourful name coined by one of its skeptics. The name stuck, and so the greatest event in the history of existence came to be known by this rather undignified moniker. As you drift deeper into the embrace of night, let your mind wander back to that first moment, 13.5 billion years ago, when time and space began. Picture, if you can, a point smaller than the smallest particle ever conceived, containing within it all the matter and energy that would eventually become every star, every planet, every grain of sand, every living creature, and every breath you have ever taken. The temperature at this moment was beyond anything that can be measured, trillions upon trillions of degrees. The density was infinite, gravity was infinite, and the very laws of physics as we understand them break down in the face of such extremes. Then, in an instant so brief that it defies description, a fraction of a second so small that it makes the blink of an eye seem like an eternity, everything changed. The universe began to expand, not into empty space, for there was no space to expand into. Rather, space itself came into being and began to grow. Time itself began to flow. The four fundamental forces that govern all of reality, gravity, electromagnetism, and the strong and weak nuclear forces, crystallized out of the primordial unity like snowflakes forming in a winter sky. This was not an explosion in the conventional sense, not matter flying outward from a central point through pre-existing space. This was the birth of space itself, the creation of the very stage upon which all future cosmic drama would unfold. In the first tiny fraction of a second, a period called the Planck epoch, the universe was smaller than an atomic nucleus, yet it contained everything that would ever be. As the universe continued to expand and cool, extraordinary transformations began to occur. The four fundamental forces, which had been unified in the primordial fire, began to separate from one another like streams branching from a mighty river. First, gravity separated from the others, then the strong nuclear force, then the electromagnetic and weak nuclear forces split apart. Each separation released tremendous amounts of energy, driving the expansion ever faster. In a process that cosmologists call inflation, the universe underwent a period of exponential expansion so rapid that it defies imagination. In less than a trillionth of a trillionth of a trillionth of a second, space expanded by a factor of at least 10^26. To put this in perspective, imagine a single atom suddenly growing to the size of a grapefruit. That atom would have expanded far less than the universe did during inflation. This stupendous growth smoothed out any irregularities in the primordial fabric of space-time and set the stage for everything that would follow. As the night deepens and your breathing grows slower and more peaceful, contemplate the next phase of cosmic evolution. The universe had grown from submicroscopic to macroscopic size, but it was still unimaginably hot and dense. The temperature was about 10^32 degrees Kelvin, a number so large that it has no meaning in human experience. At these temperatures, matter could not exist in any form we would recognize. There were no atoms, no molecules, no particles of any kind that we encounter in our everyday world. Instead, the universe was filled with a seething soup of quarks and gluons, the fundamental building blocks of matter. These particles, which today are confined within the nuclei of atoms, roamed freely through space, constantly being created and destroyed in the intense heat. It was a realm of pure energy, where matter and antimatter danced together in perfect balance, each particle immediately annihilating with its opposite, creating bursts of pure light. But as the universe continued to expand, it also continued to cool. Like a pot of boiling water gradually cooling on a stove, the cosmic temperature dropped steadily as space grew larger. When the universe was about 1 microsecond old, still unimaginably young, but ancient compared to the moments we have been describing, something remarkable happened. The temperature had dropped to about 10^12 degrees Kelvin, cool enough for quarks to begin binding together to form the first protons and neutrons. This process, called the quark epoch, marked the first time that matter as we know it began to take shape. The quarks, which had been flying free through space, were now cool enough to be captured by the strong nuclear force and bound together into composite particles. 3 quarks joined to form each proton and neutron, the particles that would eventually become the hearts of all atomic nuclei. But even as this first great synthesis was occurring, a cosmic mystery was unfolding. For reasons that scientists still do not fully understand, there was a tiny imbalance in the cosmic scales. For every billion antimatter particles, there were 1,000,000,001 matter particles. This minuscule difference, less than 1 part in a billion, would prove to be the foundation of everything that exists today. As you settle deeper into the peaceful embrace of sleep, imagine this cosmic holocaust that followed. When matter and antimatter particles meet, they annihilate each other completely, converting their entire mass into pure energy. For the first few minutes of the universe's existence, this process of mutual destruction raged on a cosmic scale. Billions upon billions of particles destroyed each other in brilliant flashes of light, leaving behind only that tiny excess of matter particles. When the annihilation was complete, the universe was left with the building blocks of everything we see today: protons, neutrons, electrons, and photons of light. The cosmic background radiation that we can still detect today with sensitive instruments is the afterglow of this great annihilation, the fading echo of the moment when the universe chose matter over antimatter. The universe was now about 1 second old, and its temperature had dropped to about 1010 degrees Kelvin, still unimaginably hot, but cool enough for the next great phase of cosmic evolution to begin. The protons and neutrons that had formed from the cooling quark soup began to stick together, bound by the strong nuclear force into the first atomic nuclei. This process, called Big Bang nucleosynthesis, lasted for about 20 minutes. It was a brief but crucial period in cosmic history, for it was during these 20 minutes that the universe manufactured the first elements. The protons, which are simply hydrogen nuclei, combined with neutrons to form deuterium, the heavy isotope of hydrogen. Some of these deuterium nuclei captured additional protons and neutrons to become helium-3 and helium-4. A tiny amount of lithium was also created. But the nuclear fires of the Big Bang could not burn for long. As the universe continued to expand and cool, the density of particles dropped to the point where nuclear reactions could no longer occur. The temperature fell below the threshold needed to fuse atomic nuclei together, and the process of primordial nucleosynthesis came to an end. When it was over, the universe consisted of about 75% hydrogen and 25% helium, with trace amounts of deuterium and lithium. This cosmic recipe, created in the first 20 minutes of time, would remain essentially unchanged for hundreds of millions of years. As the gentle night continues its passage and your mind grows calm, picture the universe as it existed after those first 20 minutes. It was still incredibly hot, about 1,000,000,000 degrees Kelvin, but it was cooling rapidly as expansion continued. Space was filled with a dense plasma of atomic nuclei and free electrons, all bathed in intense electromagnetic radiation. The photons of light were constantly being absorbed and re-emitted by the free electrons, making the universe completely opaque. Light could not travel more than a tiny distance before being scattered, like trying to see through a thick fog. For the next 380,000 years, the universe remained in this state of cosmic darkness. Though it was filled with intense radiation, no light could travel freely through space. If human eyes had existed then, they would have seen nothing but an impenetrable wall of glowing plasma in every direction. This was the Cosmic Dark Age, a period when the universe was pregnant with potential, but shrouded in opacity. But change was coming. As the universe continued to expand and cool, the temperature gradually dropped toward a critical threshold. When the cosmic temperature reached about 3,000 degrees Kelvin, still hot enough to melt copper, but cool compared to the billions of degrees of earlier epochs, something wonderful happened. The electrons, which had been flying free through space, finally became cool enough to be captured by the atomic nuclei. This process, called recombination, marked one of the most important transitions in cosmic history. For the first time, complete atoms formed. Hydrogen nuclei captured electrons to become hydrogen atoms. Helium nuclei captured electrons to become helium atoms. The universe had finally become electrically neutral, with the positive charges of the nuclei balanced by the negative charges of the electrons. More importantly, with the free electrons now bound up in atoms, the photons of light were no longer being constantly scattered. For the first time since the first fraction of a second after the Big Bang, light could travel freely through space. The universe became transparent, and the cosmic microwave background radiation, the afterglow of creation itself, began its journey through space, carrying with it the image of the universe as it appeared when it was only 380,000 years old. As you drift deeper into the peaceful depths of night, contemplate this moment of cosmic dawn. The universe was now filled with vast clouds of hydrogen and helium gas, illuminated by the fading glow of the Big Bang. The temperature was dropping rapidly as expansion continued, and the cosmos was entering its longest and most peaceful era, the cosmic dark ages. For the next several 100 million years, very little happened on the grand scale of cosmic evolution. The universe continued to expand and cool, and the great clouds of primordial gas drifted through space under the gentle influence of gravity. But beneath this apparent tranquility, subtle processes were at work that would eventually lead to the next great phase of cosmic development. The key to understanding what happened next lies in those tiny irregularities in the cosmic microwave background radiation. When we examine this ancient light with sensitive instruments, we find that it is not perfectly uniform. There are tiny variations in temperature, differences of only a few parts in 100,000. But these minuscule fluctuations were the seeds from which all the large-scale structure of the universe would grow. In regions where the density was slightly higher than average, gravity began to pull in additional matter. These overdense regions grew slowly at first, attracting more and more material from their surroundings. As the universe continued to expand and cool, these gravitational seeds became more and more pronounced. What had started as tiny ripples in the cosmic density field began to grow into vast networks of dark matter, the mysterious substance that makes up most of the matter in the universe. Dark matter, as its name suggests, does not emit light or interact with electromagnetic radiation in any way we can directly detect. Its presence is revealed only through its gravitational effects on ordinary matter and light. This invisible substance began to collapse under its own gravity, forming the first large-scale structures in the universe, vast halos of dark matter that would eventually become the scaffolding upon which galaxies would form. As the night deepens and your breathing becomes more rhythmic and peaceful, imagine the universe as it appeared during this era of structure formation. Vast filaments of dark matter stretched across space like an enormous three-dimensional web. At the intersections of these cosmic filaments, massive concentrations of dark matter began to form. The dark matter halos that would eventually host the first galaxies. But the ordinary matter, the hydrogen and helium gas that makes up the stars and planets and everything we can see, was not yet participating in this cosmic construction project. Unlike dark matter, ordinary matter can lose energy by radiating light, allowing it to cool and collapse more efficiently. But in the early universe, there were no mechanisms for the gas to cool effectively. The cosmic microwave background radiation was still too hot, keeping the gas at temperatures of hundreds of degrees Kelvin. Then, about 400 million years after the Big Bang, something extraordinary began to happen. The universe had finally cooled enough for the first gravitational collapse of ordinary matter to begin. In the deepest gravitational wells created by the dark matter halos, clouds of hydrogen and helium gas began to fall inward under their own gravity. As these clouds collapsed, they heated up, and when they reached temperatures of about 10 million degrees Kelvin, something magical occurred. The first stars were born. These were not stars like our sun, which formed billions of years later from gas enriched with heavy elements. These first stars, which astronomers call population 3 stars, were made almost entirely of hydrogen and helium. They were massive beyond imagination. Some may have been 100 or even 200 times as massive as our sun. They burned with incredible intensity, shining with the light of millions of suns, and their lives were brief and violent. Let your mind drift to this cosmic dawn as sleep begins to embrace you. Picture these first stellar beacons igniting in the darkness, their brilliant light beginning to illuminate the universe for the first time since the cosmic microwave background had faded. These monster stars lived fast and died young, burning through their nuclear fuel in just a few million years before exploding as supernovae of unimaginable violence. But in their brief lives, these first stars accomplished something of cosmic importance. In their nuclear furnaces, they began the process of creating the heavy elements that would eventually make planets and life possible. Through nuclear fusion, they converted hydrogen and helium into carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements. When they died in supernova explosions, they scattered these newly created elements throughout space, enriching the primordial gas clouds with the raw materials for future generations of stars and planets. The death of the first stars marked the end of the cosmic dark ages and the beginning of the era of cosmic rionization. The intense, ultraviolet radiation from these massive stars began to ionize the hydrogen gas that filled the space between galaxies, stripping the electrons from hydrogen atoms and making the universe transparent to certain wavelengths of light for the first time since recombination. As you settle deeper into the comfort of night, consider the profound transformation that was occurring throughout the cosmos. The universe was awakening from its long slumber. The first stars were forming in ever-increasing numbers, their light pushing back the darkness, and their nuclear furnaces manufacturing the elements that would eventually become the building blocks of worlds and life. The first galaxies began to take shape during this era, as the gas enriched by the first supernovae began to form new generations of stars. These early galaxies were small and irregular, nothing like the majestic spiral galaxies we see today. They were more like stellar nurseries, chaotic regions where massive stars formed, lived and died in rapid succession, each generation enriching the gas further with heavy elements. The process of galaxy formation was gradual and complex. The dark matter halos provided the gravitational framework, but the ordinary matter had to cool and condense within these halos before stars could form. This process was regulated by a delicate balance between heating and cooling, between the gravitational pull trying to collapse the gas and the radiation pressure from newly formed stars trying to blow it away. As the first billion years of cosmic history unfolded, the universe underwent a dramatic transformation. What had been a relatively smooth distribution of matter became highly structured, with galaxies forming at the intersections of dark matter filaments and vast voids opening up between them. The cosmic web, the largest scale structure in the universe, began to emerge. During this era, the first supermassive black holes also began to form. These gravitational monsters, millions or billions of times more massive than our Sun, appeared at the centers of many galaxies. How they grew so large so quickly is still one of the great mysteries of cosmology. Some may have formed from the direct collapse of massive gas clouds, while others may have grown from the remnants of the first generation of stars. As the night continues its gentle passage and sleep beckons more insistently, picture the universe as it appeared about 1 billion years after the Big Bang. The cosmic dark ages were over, and space was filled with the light of countless stars. The first galaxies were taking shape, powered by the nuclear fires of massive stars and the gravitational energy of accreting black holes. The universe was becoming a more complex and interesting place, with structure emerging on all scales from individual stars to vast galaxy clusters. But the story of cosmic evolution was far from over. The universe was still young, and many of the most important developments in its history were yet to come. The formation of the first planets, the emergence of life, the development of complex chemistry, all of these wonders still lay in the future. As the first galaxies continued to evolve, they began to interact with one another. Gravity, the weakest of the fundamental forces but the only one that acts over truly cosmic distances, began to pull galaxies together into groups and clusters. These gravitational encounters triggered bursts of star formation and fed the supermassive black holes at galactic centers, causing them to shine as quasars, the most luminous objects in the universe. The era from about 1 to 4 billion years after the Big Bang was marked by intense galactic activity. Star formation rates were much higher than they are today, and the universe was filled with the light of quasars and the explosions of supernovae. This was the cosmic noon, when the universe was at its most active and energetic. During this period, the first spiral galaxies began to form. These elegant structures, with their graceful curved arms and central bulges, represented a new level of organization in the cosmos. The spiral arms were not permanent features, but rather waves of star formation that swept around the galactic disk, triggering the birth of new stars and illuminating the surrounding gas with their brilliant light. Our own Milky Way galaxy began to take shape during this era. Like many large galaxies, it probably formed through the merger of smaller galaxies, a process that continued for billions of years. The disk of our galaxy, where our solar system now resides, formed as gas, settled into the gravitational well of the dark matter halo, cooling and condensing into a thin, rotating disk. As you drift toward the peaceful realm of sleep, imagine the cosmic dance of galaxies that was occurring throughout the universe. Galaxies merged and interacted, their gravitational encounters reshaping their structure and triggering new episodes of star formation. The universe was becoming more organized on large scales, with galaxies clustering together into groups and clusters connected by filaments of dark matter. But even as this large-scale structure was emerging, important developments were occurring on smaller scales as well. The first planets began to form around some of the new generation of stars. These stars, unlike the massive first-generation stars, were smaller and longer-lived, and they formed from gas that had been enriched with heavy elements by previous generations of stellar evolution. The process of planet formation was gradual and complex. It began with the formation of a protoplanetary disk, a rotating disk of gas and dust surrounding a newly formed star. Within this disk, tiny particles of dust began to stick together through electrostatic forces, forming larger and larger aggregates. These particles continued to collide and merge, growing from microscopic dust grains to pebbles to rocks to asteroids. In the inner regions of the protoplanetary disk, where temperatures were high, only rocky materials could condense. These formed the terrestrial planets, small dense worlds like Mercury, Venus, Earth and Mars in our own solar system. In the outer regions, where temperatures were much lower, water and other volatile compounds could freeze into ice, allowing much larger planets to form. These became the gas giants, massive worlds that could accumulate thick atmospheres of hydrogen and helium. 6 billion years ago, more than 9 billion years after the Big Bang. By this time, the universe had already undergone most of its major transformations. The cosmic microwave background had cooled to just a few degrees above absolute zero. Galaxies had formed and evolved into the major types we see today, and the rate of star formation had begun to decline from its peak during cosmic noon. Our sun formed from the gravitational collapse of a giant molecular cloud, a vast region of space filled with cold gas and dust. This cloud was already enriched with heavy elements created by previous generations of stars, providing the raw materials needed to form not just the sun, but also the rocky planets that would orbit it. As the night deepens and your consciousness begins to fade into the gentle embrace of sleep, contemplate the remarkable chain of events that led to the formation of our world. The carbon in your body was forged in the nuclear furnaces of ancient stars. The oxygen you breathe was created when those stars died in supernova explosions. The iron in your blood was manufactured in the final moments of a massive star's life, when the core collapsed and rebounded in one of nature's most violent events. The Earth itself formed through the gradual accumulation of rocky debris in the inner solar system. This process, called accretion, took millions of years to complete. The early Earth was a hellish world, constantly bombarded by asteroids and comets, its surface covered with oceans of molten rock. The Moon formed during this chaotic period, probably as the result of a collision between the Earth and a Mars-sized object that astronomers call Theia. Gradually, as the bombardment subsided, the Earth began to cool. Water vapor in the atmosphere condensed to form the first oceans, and the planet's surface began to solidify into the first solid crust. The atmosphere of the early Earth was very different from today's, consisting mainly of methane, ammonia, and other compounds that would be toxic to most forms of life as we know it. But even in this harsh environment, the chemistry of life began to emerge. Somewhere in the warm pools of the early Earth, or perhaps in the depths of the ocean near hydrothermal vents, the first self-replicating molecules appeared. These were not yet alive in the sense that we understand life today, but they represented the first step on the long journey from chemistry to biology. The emergence of life on Earth marked a new chapter in the cosmic story. For the first time since the Big Bang, the universe had produced something that could grow, reproduce, and evolve. Life represented a new form of organization, a way for matter to become more complex and structured over time, rather than simply decaying toward equilibrium. The first life forms were simple, single-celled organisms, probably similar to bacteria. They lived in the oceans and derived their energy from chemical reactions rather than from sunlight. For nearly 2 billion years, these simple organisms were the only life on Earth, slowly evolving and diversifying, but remaining microscopic and relatively simple. 4 billion years ago, something revolutionary happened. Some of these early organisms evolved the ability to perform photosynthesis, to capture energy from sunlight and use it to convert carbon dioxide and water into organic compounds. This innovation, which first appeared in cyanobacteria, would transform not only life on Earth, but the entire planet. As you sink deeper into the peaceful depths of sleep, consider the profound impact of this development. The oxygen produced by photosynthesis began to accumulate in the atmosphere, gradually changing its composition. This was actually a crisis for most of the life forms that existed at the time, since oxygen was toxic to the anaerobic organisms that had dominated the early Earth. Many species went extinct in what scientists call the Great Oxidation Event, but the crisis also created new opportunities. Oxygen is a highly reactive element that can be used to extract much more energy from organic molecules than was possible with the anaerobic metabolism of early life. The organisms that evolved the ability to use oxygen for respiration gained a tremendous advantage, and they began to diversify rapidly. 8 billion years ago, another crucial innovation appeared: the first eukaryotic cells. These were much more complex than the simple prokaryotic cells that had dominated life up to that point. Eukaryotic cells contained a nucleus and other specialized structures, called organelles, each with specific functions. Most importantly, they contained mitochondria, the powerhouses of the cell, which were probably once independent bacteria that had been engulfed by larger cells in a symbiotic relationship. The evolution of eukaryotic cells opened up new possibilities for life. These cells could be much larger than prokaryotic cells, and they could specialize in different functions. This led to the evolution of the first multicellular organisms, probably around 1 billion years ago. At first, these were simple colonies of identical cells, but gradually they evolved into more complex organisms with different types of cells performing different functions. For most of Earth's history, life remained microscopic and confined to the oceans. But about 540 million years ago, something remarkable happened. In a relatively short period of geological time, known as the Cambrian explosion, complex multicellular life forms appeared in the fossil record for the first time. These included the first animals with hard shells, eyes, and complex body plans. The Cambrian explosion marked the beginning of the Phanerozoic Eon, the era of visible life. From this point forward, the fossil record becomes much richer, allowing us to trace the evolution of life in much greater detail. The story of life on Earth from the Cambrian to the present is a tale of increasing complexity and diversity, punctuated by mass extinctions and followed by rapid diversification into new ecological niches. As the gentle night continues and sleep beckons more insistently, let your mind wander through the great epochs of life on Earth. The Paleozoic era saw the first forests, the first vertebrates to colonize the land, and the evolution of the first reptiles. The Mesozoic era was dominated by the dinosaurs, those magnificent creatures that ruled the Earth for over 160 million years. The Cenozoic era, which began 66 million years ago with the extinction of the dinosaurs, saw the rise of mammals and eventually the emergence of our own species. But the story of life on Earth is just one thread in the much larger tapestry of cosmic evolution. While life was evolving on our planet, the universe itself continued to change and develop. Galaxies continued to merge and interact. New stars continued to form and die. And the large-scale structure of the universe continued to evolve under the influence of gravity and the mysterious force known as dark energy. Dark energy, which makes up about 70% of the universe, is perhaps the greatest mystery in cosmology today. It appears to be a property of space itself, causing the expansion of the universe to accelerate rather than slow down, as we might expect from the gravitational attraction of matter. This discovery, made in the late 1990s through observations of distant supernovae, has profound implications for the future of the universe. The acceleration of cosmic expansion means that the universe will continue to grow larger and colder forever. 7 degrees above absolute zero will continue to cool as the universe expands. Eventually, it will become so cold that it will no longer provide any significant energy to the universe. As you drift deeper into the embrace of sleep, contemplate the far future of the cosmos. In about 5 billion years, our sun will exhaust its supply of hydrogen fuel and begin to evolve into a red giant star. It will expand enormously, possibly engulfing the inner planets including Earth. Even if our planet survives this transformation, it will be stripped of its atmosphere and oceans and rendered completely uninhabitable. But the death of the sun will be just one small event in the much grander cosmic drama that will unfold over the coming trillions of years. As the universe continues to expand and cool, star formation will gradually decline. The gas needed to form new stars will become increasingly scarce as it is locked up in planets, brown dwarfs, and the remnants of dead stars. Eventually, perhaps 100 trillion years from now, the last stars will form from the remaining gas in the universe. These will probably be small, red dwarf stars that burn their fuel very slowly and can shine for trillions upon trillions of years. But even these long-lived stars will eventually exhaust their fuel and fade away, leaving behind white dwarfs, neutron stars, and black holes. As the expansion of the universe continues, galaxies will become increasingly isolated from one another. The recession velocity of distant galaxies will eventually exceed the speed of light, making them invisible to observers in our own galaxy. Each galaxy cluster will become an isolated island universe, cut off from all others by the expanding space between them. Within these isolated galaxy clusters, the slow dance of gravitational interactions will continue. Stars will occasionally be thrown out of their parent galaxies by close encounters with other stars or by the tidal forces of merging galaxies. Some stars will fall into the supermassive black holes at the centers of galaxies, releasing tremendous amounts of energy as they are torn apart and consumed. The universe will enter what cosmologists call the degenerate era, when the only sources of energy will be the slow decay of protons and the gradual evaporation of black holes through Hawking radiation. This era will last for an almost unimaginable length of time, perhaps 10^37 years or more. During this time, the universe will become increasingly cold and empty, with vast distances separating the few remaining sources of energy. As sleep begins to overtake you and the boundaries between consciousness and dreams begin to blur, let your mind drift through these vast expanses of cosmic time. Even in this far future, the universe will not be completely dead. Black holes will continue to evaporate, though the process will be incredibly slow. The most massive black holes, those with masses millions or billions of times that of our Sun, will take longer than 10–100 years to completely evaporate. But eventually, even the largest black holes will disappear, leaving behind nothing but a thin soup of elementary particles, electrons, positrons, neutrinos, and photons, separated by enormous distances in an ever-expanding space. The universe will have reached a state of maximum entropy, with no remaining sources of free energy to drive any kind of complex processes. This is the heat death of the universe, the final fate predicted by our current understanding of physics and cosmology. It is a state of perfect equilibrium where nothing can ever happen again because there are no energy differences left to exploit. The universe will continue to expand forever, becoming ever colder and more dilute, until the temperature approaches absolute zero and the density approaches zero as well. Yet even in this seemingly final state, quantum mechanics suggests that rare fluctuations might still occur. In the incredibly distant future, after times so long that they dwarf the current age of the universe, as the age of the universe dwarfs a single second, random quantum fluctuations might occasionally create small regions of higher energy density. These fluctuations might even lead to the formation of new universes through a process similar to the original Big Bang. Some cosmologists speculate that our own universe might be just one in an infinite sequence of universes, each one born from the quantum fluctuations of the previous one. In this scenario, the heat death of our universe would not be the end of everything, but simply the end of one chapter in an eternal cosmic story. But these speculations take us far beyond the realm of established science and into the realm of cosmological philosophy. What we can say with confidence is that the universe has already lived through most of its active, star-forming phase. The peak of star formation occurred billions of years ago when the universe was much younger and denser than it is today. We are living in the mature phase of cosmic evolution, when most of the universe's matter has already been processed through the nuclear furnaces of stars. As the night deepens and sleep claims you more fully, reflect on the remarkable journey we have traced through cosmic time. From the infinite density and temperature of the Big Bang to the vast, cold expanses of the far future, the universe has undergone transformations that dwarf anything in human experience. Yet throughout this epic saga, certain themes remain constant. The interplay between order and chaos, the tendency of matter to organize itself into increasingly complex structures, and the relentless expansion of space itself. The story of the universe is also, in a very real sense, our own story. The atoms in our bodies were forged in the hearts of dying stars. The energy that powers our lives comes ultimately from nuclear fusion in the sun. The complex chemistry that makes life possible depends on the delicate balance of physical constants that were established in the first moments after the Big Bang. We are not separate from the universe, but intimately connected to it. We are made of star stuff, as Carl Sagan famously said, 8 billion years ago, with the Big Bang. In a very real sense, we are the universe becoming aware of itself, matter organized in such a way that it can contemplate its own origins and destiny. This realization fills some people with a sense of cosmic loneliness, the feeling that we are insignificant specks in a vast and indifferent universe. But there is another way to look at it. The fact that the universe has evolved in such a way that it can produce beings capable of understanding their own origins and contemplating their place in the cosmic order is perhaps the most remarkable thing of all. Consider the incredible chain of events that had to occur for consciousness to emerge in the universe. The first stars had to form and die, scattering heavy elements into space. Planets had to condense from this enriched material. Life had to emerge from non-living matter and evolve over billions of years into increasingly complex forms. Brains had to develop the capacity for abstract thought and self-reflection. Each step in this process was contingent on countless other factors, from the precise values of the fundamental constants of physics to the specific history of our planet and solar system. The emergence of consciousness represents something genuinely new in the universe. For the first time since the Big Bang, matter had organized itself in such a way that it could perceive, think, and wonder about its own existence. Through human consciousness, the universe had developed the capacity to study itself, to discover its own history, and to contemplate its own future. As you settle deeper into the peaceful realm of sleep, let your mind dwell on this profound mystery. The same physical processes that created galaxies and stars also created the neural networks in your brain. The same quantum mechanics that governs the behavior of subatomic particles also underlies the biochemical processes that generate thoughts and consciousness. In contemplating the universe, you are participating in a process that is itself a product of cosmic evolution. The scientific revolution that began in the 16th and 17th centuries represented a new phase in this cosmic awakening. For the first time, human beings began to develop systematic methods for understanding the natural world. The work of Copernicus, Galileo, Kepler, and Newton revealed that the Earth was not the center of the universe, but simply one planet among many orbiting an ordinary star in an ordinary galaxy. This gradual expansion of cosmic perspective continued through the centuries. In the 18th and 19th centuries, astronomers began to realize that our Sun was just one star among billions in the Milky Way galaxy. In the early 20th century, Edwin Hubble's observations revealed that our galaxy was just one of billions of galaxies in an expanding universe. Each discovery pushed the boundaries of the known universe farther outward and revealed new depths of cosmic space and time. The development of modern cosmology in the 20th century brought us face to face with the ultimate questions about the nature of existence itself. The Big Bang theory provided a scientific creation story that was more wonderful and more strange than any myth ever conceived by human imagination. For the first time, we had a coherent account of how everything we see around us came to be, from the largest structures in the universe to the atoms in our bodies. But with this knowledge came new mysteries. What caused the Big Bang? What is dark matter? What is dark energy? Are there other universes beyond our own? These questions push the boundaries of current scientific understanding and may require new conceptual frameworks to answer. As the night continues its gentle passage and your breathing grows slow and deep, contemplate the remarkable fact that we live in a universe that is comprehensible to the human mind. The same mathematical relationships that describe the motion of planets also govern the behavior of atoms. The same physical laws that operated in the first moments after the Big Bang continue to operate today. There is a deep underlying unity to all of physics, a set of fundamental principles that connects everything from quantum mechanics to cosmology. This comprehensibility of the universe is itself a profound mystery. Why should the human brain, which evolved to help our ancestors survive on the African savanna, be capable of understanding the behavior of black holes and the expansion of space? Why should mathematics, an abstract creation of human thought, prove to be so unreasonably effective in describing the physical world? Some philosophers and scientists have suggested that this unreasonable effectiveness of mathematics is evidence that the universe itself is somehow mathematical in nature. Perhaps the physical world we perceive is just the surface manifestation of an underlying mathematical reality. Others argue that our ability to understand the universe is simply a consequence of the fact that we are part of it. We can understand it because we are made of the same stuff and governed by the same laws. These questions take us to the very foundations of philosophy and touch on some of the deepest mysteries of existence. What is the relationship between mind and matter? How does consciousness arise from the complex interactions of neurons and synapses? Is there something special about biological systems that allows them to generate subjective experience, or could any sufficiently complex information processing system become conscious? The search for extraterrestrial life represents another frontier in our cosmic understanding. If life is a common outcome of cosmic evolution, then the universe may be teeming with conscious beings like ourselves. The discovery of even simple microbial life on Mars or Europa would have profound implications for our understanding of our place in the cosmos. It would suggest that the emergence of life is not a rare accident, but a natural consequence of the chemical and physical processes that occur throughout the universe. As you drift deeper into the embrace of sleep, imagine the possibility that consciousness has emerged countless times throughout the universe. Perhaps at this very moment, beings on distant worlds are looking up at their own night skies and wondering about their place in the cosmic order. Perhaps they too have developed science and technology and are asking the same fundamental questions about the nature of existence that we are asking. The search for extraterrestrial intelligence represents humanity's attempt to answer one of the most profound questions we can ask. Are we alone? The answer to this question will have profound implications for how we understand ourselves and our place in the universe. If we are alone, then consciousness is an incredibly rare and precious phenomenon, and we bear a special responsibility as the only known means by which the universe can know itself. If we are not alone, then consciousness is a more common feature of cosmic evolution, and we are part of a vast community of intelligent beings. Either way, the emergence of consciousness represents a remarkable achievement of cosmic evolution. 8 billion years since the Big Bang, the universe has evolved from a simple, hot, dense state to a complex system containing galaxies, stars, planets, and living beings. The same physical processes that created the cosmic web of galaxies also created the neural networks in our brains. We are intimately connected to the universe not just physically, but intellectually and spiritually as well. The story of cosmic evolution is still being written. We are living in a particularly interesting epoch, when the universe is old enough to have developed complex structures, but young enough that stars are still forming and galaxies are still evolving. The cosmic microwave background radiation that we observe today carries information about the state of the universe when it was only 380,000 years old. By studying this ancient light, we can learn about the conditions that prevailed in the early universe and test our theories about cosmic evolution. Future observations will continue to push back the frontiers of our cosmic knowledge. The James Webb Space Telescope and other advanced instruments are already revealing new details about the formation of the first galaxies and the early epochs of star formation. Ground-based telescopes are discovering thousands of exoplanets, giving us our first glimpse of the diversity of planetary systems throughout the galaxy. As the night deepens and sleep claims you more fully, consider the remarkable journey of discovery that has brought us to our current understanding of the universe. Less than a century ago, we didn't even know that galaxies other than our own existed. We had no idea about the expansion of the universe or the Big Bang. We knew nothing about dark matter or dark energy. The entire field of cosmology was in its infancy. Today, we have a detailed understanding of cosmic evolution from the first fraction of a second after the Big Bang to the present day. We know how the first atoms formed, how the first stars ignited, how galaxies assembled, and how the elements essential for life were created and dispersed throughout the universe. This knowledge represents one of the greatest intellectual achievements in human history. But with this knowledge comes a new sense of responsibility. We now understand that we are part of a cosmic story that is much larger and more ancient than human civilization. 8 billion years, and it will continue to evolve for trillions of years into the future. Our species has existed for only a tiny fraction of cosmic time, yet we have already gained the ability to understand our cosmic origins and to contemplate our cosmic destiny. This perspective can be both humbling and inspiring. It reminds us that we are small and temporary beings in a vast and ancient universe, but it also reveals that we are part of something magnificent, a cosmic evolutionary process that has produced not just galaxies and stars, but also life and consciousness, and the capacity for wonder and understanding. As you sink deeper into the peaceful depths of sleep, let your mind rest in the knowledge that you are part of this cosmic story. The same atoms that were forged in the hearts of ancient stars now form your body. The same fundamental forces that shaped the large-scale structure of the universe also govern the biochemical processes that sustain your life. In a very real sense, you are a temporary arrangement of cosmic matter that has developed the remarkable ability to contemplate its own origins. The universe began as a point of infinite density and temperature, smaller than an atom, but containing all the matter and energy that would ever exist. 8 billion years since that first moment, it has evolved into something unimaginably vast and complex, filled with billions of galaxies, each containing billions of stars. And at least once, on a small rocky planet, orbiting an ordinary star in an ordinary galaxy, this cosmic evolution has produced beings capable of understanding their own origins and place in the cosmic order. This is perhaps the most remarkable fact of all, that the universe has evolved in such a way that it can know itself. Through human consciousness and scientific investigation, the cosmos has developed the capacity to study its own history, to discover its own laws, and to contemplate its own future. We are the universe becoming aware of itself, matter organized in such a way that it can perceive and think and wonder about its own existence. The final saga of this cosmic story is still being written. The universe will continue to evolve for trillions upon trillions of years, long after our sun has died and our galaxy has merged with others. The processes of cosmic evolution that began with the Big Bang will continue until the last stars fade and the last black holes evaporate into the cold emptiness of space. But the emergence of consciousness represents something genuinely new in this cosmic evolution. For the first time, the universe has produced beings capable of understanding their own origins and contemplating their own place in the cosmic order. Through science and philosophy, art and literature, we are participating in the universe's ongoing attempt to understand itself. As the gentle night embraces you and consciousness fades into the realm of dreams, rest in the knowledge that you are part of this cosmic awakening. 8 billion years ago with the Big Bang and continues to unfold with each passing moment. The universe began in simplicity and has evolved toward complexity. From the primordial fireball of the Big Bang to the intricate networks of neurons in your brain, cosmic evolution has produced structures of ever-increasing sophistication and beauty. You are both a product of this evolution and a participant in it, a conscious being capable of contemplating the cosmic story of which you are a part. In the vast expanse of space and time, in the grand saga of cosmic evolution from the Big Bang to the present moment, consciousness has emerged as perhaps the most remarkable phenomenon of all. Through your thoughts and dreams, through your capacity for wonder and understanding, the universe has developed the ability to know itself. You are the cosmos made conscious, a temporary arrangement of star stuff that has awakened to contemplate its own magnificent origins in the infinite darkness from which all light and life and consciousness have emerged. Still haven't fallen asleep? Here is some calming rain sounds to help you fall asleep.